The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Last class, we introduced thin film technologies. We described some of their generic advantages and disadvantages. I showed that particular book that's going around in the back there, the Handbook of Photovoltaic Science and Engineering. That describes several of the technologies that we're discussing today and last class. So last class, we covered general thin films and CadTel, cadmium telluride. Today, we're going to be talking about amorphous silicon, copper indium gallium diselenide, and a last material system, which is actually more of a stack or a composite of several. Then we'll enter a debate, which will be kind of fun. So amorphous silicon. We talked about crystalline silicon. Crystalline silicon is the crystalline form of the element known as silicon, comprising a diamond cubic crystal structure. Amorphous silicon, on the other hand, is a very broad term catching a range of materials that lack long-range order. Let me be a little bit more specific. Typically, there is some semblance of short-range order in these materials. One can describe the composition of amorphous silicon using, say, for example, a radial distribution function, the average distance from one atom to the next, and you have these distribution functions describing the material. It gets a little bit more tricky when you try to define it on a more detailed level with average number of nearest neighbors, the local configuration, the number of stretched bonds locally. And the reality is that with any amorphous material, you can deposit a range of materials. It isn't just one specific amorphous silicon material that you get every time. Depending on your deposition conditions, depending on the pressure and the temperature and the power during the PECVD, the plasma enhanced chemical vapor deposition, you obtain a range of amorphous silicon materials. And that range, or within that range, you can find that the mobility of charge carriers can vary by several factors. The mobility, I believe, in amorphous silicon can range easily between 0.001 and 0.1 centimeters squared per volt second. So that's 2 orders of magnitude easily. And I have heard of amorphous silicon materials that have gone as low as 10 to the minus 4 centimeters squared per volt second and as high as approaching 1. So we have a range of material qualities as a result, and also a range of performance. Likewise, there's a range of stress in the film, depending on how you deposit your amorphous silicon. Delamination is of concern as well, depending on how you deposit it. And the challenges from a material level is getting a consistent quality material, high quality material, every single deposition, and overcoming certain degradation modes that are present in amorphous silicon, not present in other material systems, certainly not present in crystalline silicon. For example, the Stabler-Wronski defect. That's still up for some debate as to what precisely is the atomic nature of that defect, but it is known that when one exposes amorphous silicon to sunlight, that the performance will degrade with a relatively quick time constant over the period of minutes and hours, and finally stabilize. So when you report the cell performance of an amorphous silicon cell, it's always very important to emphasize that this is light degraded or light stabilized efficiency, as opposed to the efficiency you get when you take it straight out of the deposition chamber and it hasn't been exposed to high amounts of sunlight yet. In general, amorphous silicon has low hole mobility. Again, the precise root cause on an atomic scale for the low hole mobility is still up for some debate. There's a professor here at MIT, Jeff Grossman, who has performed a combination of molecular dynamics and density functional theory to obtain amorphous silicon samples in DFT. And through those samples, he was able to determine, he and his colleagues were able to determine that the low hole mobility might be caused by stretched bonds, certain types of stretched bonds within the amorphous silicon. There are other hypotheses out there as well in the literature. Finally, just getting a uniform film deposition at high speed. That's really a key. A high-speed uniform deposition of this layer has proved challenging in commercial production so far. So all of this has combined so that amorphous silicon has received a lot of attention, but hasn't yet, in a massive way, been economically successful. This is a cross-section, SEM, of an amorphous silicon device showing the TCO, the transparent conducting oxide, on the top. The TCO was deposited onto the glass, which appears at the very top underneath the scale bar. The amorphous silicon layer right here in the middle is shown. It is in a PIN structure. So we've learned about P-N junctions. The I layer in between is an intrinsic layer, meaning lightly doped. And this, we'll see the band diagram on the next slide. The silver contact on the back here extracting the charge from the backside. So this is an example of the amorphous silicon technology. Again, another cross-section, just for your reference, showing the stack there. OK, the PIN device architecture. Right here, we can see the P plus layer, or the P layer, the N layer, and then the I here in the middle, the lightly doped intrinsic layer. Note the band structure, or the band diagram, how it's arranged. And interestingly, the layer thicknesses here are in the order of 300 nanometers for the entire stack. It's rather thin, typically under a micron in thickness. The reason it's very thin is because amorphous silicon absorbs light much, much better than crystalline silicon. For those who have a solid-state physics background and want to know the root cause of that, I'll explain briefly. For those who don't have the background and can't follow, don't worry. Plant a flag. We'll come right back to it. So in crystalline silicon, we have crystal symmetry, and hence we have momentum conservation rules when we excite charge carriers, hence the indirect bandgap nature of crystalline silicon. When we amorphize our material, we no longer have that crystal symmetry. We no longer have momentum conservation. We can excite directly from your valence band into your conduction band. So that, in a very quick hand-wavy way, is why amorphous silicon tends to behave like a direct bandgap semiconductor, absorbing light extremely well with a very high optical absorption coefficient. Hence, instead of 100 microns, we can get away with 300 nanometers of thickness. All right, back to our flag. We see here the PIN structure. Everybody should be able to follow along and understand that if light excites a charge carrier here in the middle, the electrons will be swept to the right, the holes to the left, and we'll have charge separation occurring. Sometimes we can have a stack of materials, like shown here, with varying band gaps by, for example, blending germanium into the amorphous silicon. This can modify the band gap of the material, and we can wind up with a stack of layers. Or we could simply use two layers of the same material. We wouldn't necessarily be able to absorb more efficiently across the solar spectrum, but we would be able to increase the voltage output of the device. So there's a variety of different amorphous silicon, shall we say, designs out there on the market. Here's one example of the triple stack. We have amorphous silicon here at the top with a large band gap. The band gap is somewhere in the range of 1.7 eV. Yep, question?
Yeah, I just have a question on how that works. So does the electron hole pair have to go to the interface between P-type and N-type material to separate?
Yeah. So in this particular case, I believe this is a dual terminal device, which would be rather tricky to perform an operation. Well, you have to imagine this is right here with very small perturbation. If you imagine it being biased in sunlight, then you can easily see how a larger voltage would result. Right here, you can imagine a two-terminal device where you extract charge from here and here, or perhaps a four-terminal device, which is less common because it requires more metal contacts, but that would contact the device here, here, again here, and here. So you'd have the two devices contacted. If you have a two-terminal device, one can typically think about it as adding the voltages together. Then the current would be limited by the worst performer of those two. And that's why you have this thinner than that one over here. Because we know that the light tends to be absorbed preferentially near the front surface, we're absorbing an equivalent number of photons in this thickness and in that thickness. So the currents tend to be matched. So that's why I would guess, given the geometry, the fact that we have silver on the back and TCO on the front, and no explicit contacts here in the middle, that this is a two-terminal device as opposed to a four. This stack right here is representative of what is commercialized by Unisolar, a company in Michigan, where we have an amorphous silicon layer on the top, wide bandgap semiconductor, somewhere in the range of 1.7 to 1.9 EV, depending on the deposition conditions. Again, I mentioned that amorphous silicon is really a range of materials. There is no one amorphous silicon. It's depending on the density of atoms inside of the amorphous structure and their local configuration, you can vary the properties quite a bit. So the band gap can vary, but typically it's in the range of 1.7 to 1.9 eV. Blending in germanium, germanium being a bigger atom, tends to reduce the band gap of the material. And you have successively higher concentrations moving toward the back. So the band gap shrinks from front to back. And you can wind up with a stack like this. And this is an example here of a 3-cell stack where you have the combined quantum efficiency and the individual quantum efficiencies of each of the subcells, showing you how you can really fill up the entire solar spectrum using a combination of these materials. Unfortunately, despite all these efforts, the material is still affected by what's called the Stapler-Wronski effect in honor of the people who initially determined it. What the Stapler-Wronski effect typically manifests itself as a degradation of material performance as a function of time. It's also known that as the layer thickness increases, the predominance of this effect also increases, and its impact also increases. So it manifests itself as a reduction of the fill factor, reduction of performance, and we see the trade-offs during device design of amorphous silicon. So that's, would say, the essence of amorphous silicon is that it's a very promising material, has a wide degree of tunability, but the low hole mobility limits its performance to somewhere around 10% for just a single amorphous silicon layer, and in the low teens for these stacks of multiple materials one on top of another. This right here is showing an interesting effect when you begin heating up your substrate. When you're depositing amorphous silicon, you have amorphous material. If you heat up your substrate to too high of a temperature during the deposition process, and this is also impacted by the concentration of silane gas to hydrogen ratio during the deposition process, one can obtain a phase transition from amorphous material into what's called microcrystalline material. That's shown at the very top. ASI stands for amorphous silicon, μSI for microcrystalline silicon. Microcrystalline silicon is right at the phase transition between an amorphous silicon and a crystalline variant, polycrystalline variant of silicon. And in some cases can actually contain a mixture of both amorphous and crystalline regions. And so it's very tricky to nail the deposition conditions just right. Somebody along the way figured out, well, wait a second, we can actually use this microcrystalline silicon to our advantage and stack a layer of microcrystalline silicon on the bottom, put a layer of amorphous silicon on the top, and that was called micromorph technology as a result. And there are companies that have commercialized micromorph. Excuse me? Sneeze right there. So the micromorph technology, commercialized by Oerlikon and previously by a company in the United States called Applied Materials. And we'll get to that in a couple of slides as well. This right here is a brief slide just addressing the issue of how growth conditions can impact material quality. There are a number of growth parameters, shall we say, that impact whether you obtain an amorphous material with high mobility, with low mobility, a microcrystalline material, nanocrystalline material, and so forth. And if you're interested in more details, these NREL reports from the late 1990s and early 2000s, mid-2000s, are really a treasure trove of information if you really want to get up to speed quickly on how to grow high-quality amorphous silicon layers. OK, so these are record amorphous silicon cell efficiencies. This, I believe, was from the Martin Green tables that come out each half year in Progress in Photovoltaics. So he and his colleagues produce an article every half of a year in Progress in Photovoltaics describing the record efficiencies of lab-sized cells, maybe a centimeter squared, all the way up to full-size modules. So we have here amorphous silicon and the blended amorphous silicon germanium, or CIGS for short. People sometimes call silicon germanium CIGS. So we have a variety of different types shown here, and the areas of the devices shown here. I would caution overinterpretation of the very small area devices. If you're at 0.25 centimeters, you're at a very small linear dimension along the side of the cell. And you can wind up being impacted by edge effects. There's also sometimes this is the active area of a much larger device where they've shrunken down the aperture. But depending on the texturization of the surface, you still get light trapping and essentially a larger active area than what is actually being shaded off. So I would caution you against overinterpreting these very small area measurements. 1 centimeter squared larger, you're typically in a regime where the results are more believable. The JSCs shown here, VOCs shown here. Note in certain cases, the VOC you would expect from amorphous silicon, if it's a bandgap of 1.7 eV, you would expect a VOC somewhere in the range of maybe 1.4 volts. And sometimes you get much lower than that. Likewise, the short circuit current is rather low, say, compared to a crystalline silicon device because of that higher bandgap, the inability to capture some of those lower energy photons. And so the record single amorphous silicon device performance, somewhere in the, buttressing up against 10%, not quite. And then if you combine different layers into a stack, for example here, you can move into the low teens for your performance. Flag that, these numbers here. We're going to get back to this and use that to understand why some of the technologies didn't make it to commercialization. This represents the largest scale attempt to commercialize amorphous silicon technology. This was a turnkey line. Let's start from over here. This is a human being seated at a computer, 2 humans. This pod right here, this machine, represents one of these little components right here that fits into a much larger assembly line. This is the PCVD reactor. Actually, I believe there were 7 of them attached to each of these little pods right here. So the plasma-enhanced chemical vapor deposition reactors were depositing microcrystalline silicon and amorphous silicon onto sheets of glass that were as large as you could possibly transport. Does anybody just happen to know the number off the top of their head? What is the largest sheet of glass that you can physically transport, say in commercial form, such that you could buy it in bulk without custom design of the Pilkington float glass process?
As big as like the cross-sectional area of that?
It's about, yeah, definitely. That's a good place to start. It's actually dictated by what can fit on some of the trucks that transport the glass back and forth. So you've ever seen the glass transport trucks with the sides where they put the panes of glass in, and they're the chassis of the truck like so, and the glass along the edge. It's around 3 by 3.3 meters. And so these deposition systems could incorporate huge sheets of glass, and then it would leave it up to the customer whether they wanted to quarter them and make reasonable size modules, or whether they'd want the full size module and have to use cranes to install them, which would reduce the labor content of installation, but would shift the burden onto the automation. So you see the panes of glass coming along, pre-cleaning and eventually insertion into these devices. Why so many of those devices? Why so many PCVD reactors, like little piglets around a pod here? They were, each of these reactors would have, say, a cycle time somewhere in the order of a few tens of minutes. So my estimate would be somewhere between 20 and 30 minutes, maybe up to 40, because the microcrystalline silicon layer just took so long to deposit. But without that microcrystalline layer, it was difficult to reach 10% efficiency. With just the amorphous silicon layer, the efficiencies were in the range of 6 to 7%. And if you start doing calculations for a 6 or a 7% module, you realize very quickly that the cost of the glass and the encapsulants and everything else adds up, because your device is so low in efficiency that you need more encapsulant, more glass, more labor, more installation to produce a panel, to produce the same amount of power. And as a result, the system cost was very high. This technology couldn't compete once the Chinese production started really ramping up in the market and decreasing the cost of traditional crystalline silicon modules. And the SunFab project, which was Applied Materials' name for this, amorphous silicon line, or micromorph line in reality, was shut down recently, relatively recently, about a year ago, when it was realized that this was no longer commercially viable in the face of some of the low-cost competition from crystalline silicon. All that could change very quickly if somehow one of you were to develop a way to, say, double the record efficiency number. So if someone were to figure out why exactly whole mobility is so low, impairing transport inside of these materials, in principle, one could then envision rolling it out into the SunFab line. There's already a turnkey production equipment that's been built by Applied Materials, ready to go, and you're off and running. So that's an opportunity out there. This lists some of the commercialization attempts. And the bottom line, in the end of the day, was that 6% modules were too inefficient to be profitable unless you reach scales of, say, gigawatts. And believe it or not, there was one company out there called OptiSolar. The business plan was literally to scale up to a gigawatt, faster than everybody else. And even though it was lower performance, the sheer size and scale of the manufacturing facility would reduce the cost of the amorphous silicon relative to crystalline silicon competition. Unfortunately, OptiSolar didn't make it either. So the companies that are left today producing amorphous silicon include Oerlikon. This is a Swiss company that produces turnkey equipment, and Unisolar, which is selling the actual modules of amorphous silicon. They have a nice roll-to-roll deposition process on these stainless steel foils. Very nice factory. I believe it was toured by several of our members of our current administration, and they're still going. Yeah.
Is the roll that that person's holding, is that the, what is it? What is he holding?
I could easily think, based on the color, that this already has amorphous silicon deposited onto it, but it could be at some intermediate phase. I don't know for that specific roll. But in principle, yes, at the end of their manufacturing line, they'll have a full stack, the triple amorphous silicon and then the 2 layers of CIGS beneath it.
It's like the base is flexible, so what's the thing that the film is deposited on?
Oh, so what they incorporate their flexible material into typically, well, one of their products is roof shingle. That looks very similar to a standard asphalt-based roof shingle, and it is very nice building integrated technology. I happened to see one back in when I was a graduate student, and I was inspired by the building integrated potential there. Mm-hmm. So there are attempts to integrate amorphous silicon into regular crystalline silicon technology as well. It turns out amorphous silicon passivates the surfaces very nicely. And you can create what's called a hit cell structure, which is a heterojunction with a thin intrinsic layer, using a silicon substrate. Typically what's used is an N-type base, and then the amorphous silicon layers are deposited on either side. And that device is currently being commercialized by a company called Sanyo in Japan. The patents for the base hit cell structure expire very soon, if they haven't expired already. And so there is a fair amount of interest. Several companies out there right now attempting to reproduce this process, but it is fairly tricky. And again, a lot of it boils down to managing the interfaces, making sure that the interface between the silicon, the crystalline silicon, and the amorphous silicon are of high quality. So we have our hit cell structure here. Let me hop over to the last thin film material so we have adequate time for our debates. The copper indium gallium diselenide, or CIGS for short. This is a quaternary phase, sometimes comprised of even 5 elements. But let's show, this is the chalcopyrite structure right here with copper shown in black, indium or gallium shown in gray. Typically there's some blend between the two. And the chalcogen, the selenium or sulfur shown in the white right here, typically selenium. So we have here an example of the crystal structure. As I understand the situation, this crystal structure came into being because copper sulfide demonstrated potential as a photovoltaic material early on, say in the late 1970s, early 1980s. There were attempts to grow high-performance copper sulfide cells. They failed because copper electromigrated. In the presence of an electric field, copper, a very small ion, far to the right on the 3D series of elements. So if you look at the transition metals, copper is on the far right, meaning you're adding more and more and more protons to the nucleus as you go from left to right, and you're pulling the outer shell in. So if you look at atomic radius going from left to right in the periodic table, you'll see that the atoms tend to shrink. So copper being on the far right-hand side of the 3D elemental series has a smaller atomic radius compared to, say, iron or manganese or titanium. And as a result, it could move fairly easily throughout the lattice if it is present in a charged state, if you have, say, copper plus, and a large electric field distributed across a thin film solar cell device. So copper sulfide devices ended up degrading quickly over time, and it was realized that some heavier elements needed to be included to stabilize the crystal structure. So in the lab, the reason why CIGS, this particular material right here, is so interesting is because in the laboratory, efficiencies on the order of 20% have been achieved. For large area, you'll have to correct this number right here. You can increase that to 15% plus. 15.7% in fact, over large area devices. That's a very recent result coming out of Miasole company in California. There are dozens of startup companies focused on CIGS development, and it is a very challenging problem to get the stoichiometry right and to passivate the defects inside of the structure, including surfaces. Where many companies fail or fall short is getting the stoichiometry just right over a large area. It's as simple as a manufacturing challenge. The idealized structure of these thin film devices, you have your CIGS layer right here in the middle. In this case, it's shown as CIS or cis, but you can add gallium as well. Typically, gallium is blended in. Moly, molybdenum, back contact on the glass. The glass in this case is just the support for the structure. Molybdenum here would be non-transparent, to be opaque layer. The cadmium sulfide on the front side here forms a very nice interface with the CIGS layer underneath, preventing any interface damage or any segregation, say, of gallium to the surface here. And then the zinc oxide layer on the top, which serves as the buffer window layer, depending, is then deposited on the cadmium sulfide layer, and eventually charge is brought away. This right here is another three-dimensional rendition of the same. What is unique about each of those dozens of startup companies is the process in which they deposit the CIGS layer, typically. So you have companies like Miasole that are invested in sputtering of CIGS. You have companies like NanoSolar that are invested in ink-based printing of CIGS. So they print an ink down, and then they sinter the ink to form the layer. And like those two, there are many other companies out there that are depositing CIGS in some way, shape, or form. The folks at NREL seem to be more in favor of a thermal evaporation-based process for CIGS. Many of the more successful industrial renditions of CIGS right now, at least the ones that appear most promising, are using other deposition methods. So you'll see a variety out there of deposition methods for CIGS technology. And one of the things to keep track of as you watch and monitor all of these startup companies is to bin them by their process and to begin to discern trends as we start to see some market leaders evolve in the sector, begin to discern which technologies are the most appropriate, perhaps for large-scale deposition of this material system. Interfaces are critical. Here are some examples of attempts at mapping out, and quite successful, attempts at mapping out the, shall we say, the band diagram of a CIGS-based solar cell. One thing to keep in mind is that just like amorphous silicon represents a broad class of materials, CIGS also represents a broad class of stoichiometries, meaning the ratio of indium to gallium, the ratio of, if you include it at all, sulfur to selenium, is critical in determining the properties of both the bulk and the surfaces. Typically at the surfaces, you will get termination by one atom, one atomic species or another, one elemental species or another, and that will determine to a large degree the electronic quality of that surface. So for a long time in literature, you had debating worldviews of what the band diagram of a CIGS device really looked like, and it turned out a lot of people were right. They just had varying starting materials, so they were comparing apples to oranges. The thing that keeps people going with CIGS is that in the laboratory, efficiencies, I believe now up to 21% have been demonstrated. So that is really encouraging. I mean, people, venture capitalists will look at this and say, wow, with those high efficiencies, you could really make solar cheap. The amount of, again, glass and capstone, labor, and so forth that you have to have per watt peak is lower because the cell can perform at a higher performance. But the downside is there's a substantial gap between what is commercially manufacturable today and that record efficiency device. Sometimes the practical matters of commercialization are the ones that impede a technology from getting to market. And I have some modicum of faith that CIGS will make it. But if it fails to reach its true market potential, if it fails to realize its dream of becoming a significant fraction of all solar panels produced, it will most likely be because of these process engineering issues associated with depositing over a large area, coupled to the scientific, I would say, gap in managing interfaces properly. So that's the story of CIGS in a nutshell. There are some minor issues, shall we say, associated with cadmium. There are attempts to go to an we're right here, to an all zinc oxide, or maybe a graded zinc oxysulfide buffer and window layer here in the front to get rid of the cadmium. We'll discuss that shortly. There are, yeah, I would say that's probably the biggest near-term challenge. With the removal of cadmium, you can access more markets. And secondly, CIGS does contain indium, which is not an infinite supply in Earth's crust. It's debatable how much of an issue that really is, and we'll get to that in our discussions as well, in our debates. CIGS commercialization. Several startup companies, and I would say a lot of promising research and development going on right now. This particular technology right here, shown, let's keep this company nameless for now. This company represents some of the difficulties in ramping up large area CIGS. They deposited sometimes over large areas, but would achieve inhomogeneous results. And so the ultimate form factor for the devices was to chop them up into areas that are not too dissimilar from an actual crystalline silicon device. So to chop up their layers into individual discrete cells, and then to connect them, solder them together, much like a crystalline silicon device would be put together inside of a module. So the dream of having this inline thin film process, roll-to-roll, was reaching an abrupt wall, shall we say, in the development process because of the lack of large-scale uniformity. So you need to chop them up into smaller units, which would add to the cost, which would decrease the module performance as well, because now you have gaps in between the cells. So it just goes to show the difficulty of bringing a new technology to market. And hopefully they're doing better now. Lots of promising news for CIGS. I like this particular article, The Rise of CIGS Finally, ? There's always been a lot of promise in the realm of CIGS because of the high performance and the high efficiencies reached. The big question is, can you accomplish this at large scale for large area modules? That's been the big challenge so far. And of course, materials availability. So let me pause right here. What I'm going to do, we are going to shift gears. And for the next 20 minutes, unfortunately not half an hour, but for the next 20 minutes, we are going to enter debate mode. What we're going to do is divide the group into, this group right here, into your project teams, and you'll cluster together and work together on this next exercise. So for the very beginning, we're going to have the cadmium Telluride debate. That will be debate number 1. We'll be discussing the pros and cons of CadTel. Keep in mind that First Solar, a gigawatt company, meaning one of the largest companies in the world, and certainly the largest company in the United States, is going full force producing cadmium Telluride modules. The debate question that you'll be faced with is it a good investment for the United States? Say, for example, you're in charge of US government research and development funds. Should you be putting your money into CadTel, or should you be putting your money into something else? And we'll have two sides of the debate, one that will defend CadTel and say, no, it's a very promising technology, we should be going all in, and the other side that will be adopting the counter-argument saying, well, CadTel has these concerns, perhaps we should be looking elsewhere to invest. And that's the debate number 1, CadTel, no CadTel. For the folks working on earth-abundant materials, the second debate will be focused on that question. Recently, there's been a lot of interest in developing earth-abundant alternatives to, say, CIGS because of the indium content and CadTel because of the tellurium content. And there's been a huge amount of momentum behind it, but there are a few naysayers out there who say, well, wait a second. We've always come up against shortages of one kind or another. Since the days of Malthusius warning about the limits of population growth because of limited food supply, but then we developed fertilizers. And that overcame that limit. Likewise, in these resource abundance issues, I'm sure we're going to find some new way to extract the metals. We'll find a way around it. We'll discover new deposits and so forth. You hear similar arguments in the peak oil debate, right? And so what I'd like to do is to set up two teams there as well to debate this particular question. And we furthermore recognize that several of these issues that might appear black and white in reality have many shades of gray in PV. This CAD-TEL debate is one of them. We'll hear the second debate the next time. And anything from should we invest in silicon technology or should we develop thin films will have these shades of gray as well. So it's important you recognize that simple fact as you gain maturity and shades of gray in your own ability to argument one side or another. So thank you, and we'll see us on Thursday.